In the light of increasing electricity demand, international agreements to reduce greenhouse gases limiting the use of fossil energy. Environment problems that the fact in most European countries the sites for large hydropower are almost exploited. There is an increasing interest in developing small hydropower. Entities like the EU Commission and the Directive 2001 expected the use of renewable energy to grow up to 12% and 22% respectively by the year of 2010 in the EU. The directive even goes as far to consider the small hydropower as the best proven renewable energy technology. Nevertheless, there are many barriers to overcome in order to increase the use of this natural source of energy. One of the needs in order to strengthen its competitiveness is to become more economical, and this is the main focus of the article presented here.
Classification of hydropower plants. The categories that are commonly used to define the power output of the hydropower plants are large, medium, and small hydropower plants. And two more. We have the mini and the micro hydropower plants. This paper focuses on the last two of them because mini and micro hydropower plants cause less environmental damage. Because by due their sizes, sometimes they don't need to change or alter the normal course of the river.
As known from fluid mechanics, the theoretical available power from a given head of water is directly proportional to the flow of water and the head of the water. Most turbines and generators have efficiencies of about 70%, meaning that if we had a given head of water of about 20 meters and a flow of 0.04 cubic meters per second, with this combined efficiency we would have an estimated output power of 5.5 kilowatts instead of 7.8 kilowatts. This shows that power from a given site can be very small, and such places would need to be as simple as possible without compromising the reliability of the plant.
Generator topologies. Depending on the characteristic of the network supply, a choice can be made between synchronous generator and asynchronous generator. But the first one, synchronous generator, equipped with a DC excitation system, associated with a voltage regulator to provide frequency and phase angle control before the generator is connected to the grid and supply the reactive energy required by the power system when the generator is tied into the grid. Synchronous generator can run insulated from the grid and produce power since excitation is not depending through the grid.
The second one is the asynchronous generator. They are simple squirrel cage induction motors with no possibility of voltage regulation and running at a speed directly related to the system frequency. They draw their excitation current from the grid, absorbing reactive energy by their own magnetism. Adding a bank of capacitors can compensate for the absorbed reactive energy. They cannot generate when disconnected from the grid because such generators are incapable of providing their own excitation current. In this paper, we consider a self-excited generator topology which utilizes an auxiliary stator winding with an adjustable capacitor connected to it. The stator also carries a distributed winding with design such in a way that higher order harmonics are reduced or even eliminated. Rotor laminations, however, are stamped in such a way that significant reluctance effect is produced. This feature would have an effect on the dynamic operation of the generator. Advantages of the proposed generator are the following. They are simple and robust, since it lacks of sliding contacts or a dedicated exciter. They have improved waveform from the voltage regulation via control of a stator excitement current, and they also have a improved dynamic performance and stability because of the reluctance effect.
The experimental investigation. The paper do an experimental investigation. Why? Because the investigation allows verify the concept of the self-excitation and to identify the behavior of the different design parameters too. The experimental machine selected is a standard 6 wiring AC machine with 8 of diodes. The diagram is the next one. The operation process is described as follows. Start up the DC machine. Its speed is adjusted to the synchronous value. 2. When the generator starts rotation, a small voltage is induced at the stator winding. 3. This residual voltage results in a current to flow in the stator auxiliary winding, which is short-circuited by a capacitor. 4. The auxiliary winding current sets up a pulsating magnetic field in the air gap. 5. This field current with rotor rotation causes a voltage induced in an auxiliary winding. 6. This increases the induced rotor voltage and field current. And last but not least, the same process repeats and repeats until the steady state condition is achieved.
Oh, do you want to know about the results? Okay, so even though the value of the auxiliary winding capacitance has a profound effect on the generator's steady value state operating conditions and also determine whether or not its self-excitation can be achieved, it is beyond of this scope of this paper the determination of the critical value of the capacitance. From this figure, we conclude that it takes approximately 2 cycles of the fundamental frequency for the output voltage to reach steady state. Also, the generated voltage contains higher order harmonics, and in order for this design to be practical value, this waveform must be improved by designing both the auxiliary capacitance and the load winding. Similarly, the field current reaches steady state in about 2 cycles, as illustrated in this figure. By connecting a variable resistance was determined the load characteristics in the main winding terminals, so were the RMS voltage and current value recorded when varying the resistance in this figure. The voltage drops as soon as we start to increase the load as expected. In this case, the machine got up to 12% voltage regulation from 286 volts to 252 volts. Yet again, this drop can be kept between allowable limits by adjusting the value of the capacitance in the auxiliary winding.
As the main conclusion for this paper, the use of mini and micro hydropower generation is a possible way to reduce the increasing environmental impact caused by the bigger power plant generator and create actually a sustainable energy.
2 main problems were addressed with this type of generation: the waveform of the voltage that could be solved by tailoring the winding design, and the excessive voltage regulation that can be solved by adopting a suitable control scheme.